pump engine ratio. So let's say piston engine area, engine piston area, piston area equals AE. Okay, piston area AE. A middle rod area, this is middle rod, that will be connected to your pump, right? This is a pump piston, this is engine piston. Okay, so this pump piston area AP, this area is AP. Okay, this is AE, engine area. Pump piston area AP. So P by E equals AP AE minus AMR. Okay, this is the standard formula. You have to remember piston area divided by area of engine minus area of middle rod. Okay, because middle rod will have like this, so total volume will be different. So pump with balanced middle rod, with balanced the formula will change. P by E equals AP minus AMR divided by AE minus AMR. Okay, a high P ratio requires lower power fluid volume. A high P by E ratio requires a higher requires lower power fluid lower power fluid volume. So in surface, when you are pumping, the two options are there. You have central power fluid conditioning, and one is self contained power fluid, PF, not PE, PF conditioning. The success of an economical operation is based on whether it is self-contained power fluid conditioning or centralized. Centralized means you have many wellbore and you have one centralized system, and you have one whole system is there, and manifold will be there to control the flow rate, and using that one you are delivering fluid. Okay, there are two types basically for installations: fixed type and free type. In free type, the system will be looking like this. You have one tubing, okay, and you have one bottom valve here, standing valve, okay, and you have another tubing or flow line is going to the surface. Okay, let's say initially there is no pump. Now you put one pump here. Okay, so pump will be like this. Just I am drawing a rough figure, and you have as usual on standing valve, and your side flow line is here. Okay, and this flow line is connected to here, and it is going like this. Okay, so pump is in, and you are giving very high pressure here. Okay, high pressure is here. Power fluid you are giving. Power fluid is you are pumping, and pump is going down to your exact location. Okay, so this is actually free type installation. When you change, you want to install, just using power fluid, you pressurize, the system will move on. So normally this free type system will not be used for your engine pump type system. It should be used for your jet pump type system. Okay, So this free type system also, there will be the casing free design, and there will be parallel free design, Okay, so these are OFP installation, open power fluid, OPF, right? Open power fluid installation. Okay, these two. And another is fixed, sorry, this is free type, I put wrongly, and fixed type. Okay, in fixed type what happens, your tubing and pump will be fixed on tubing, so you are not making it free with power fluid. Okay, so fixed type installation, concentric installation, fixed concentric installation option will be there, and fixed casing type will be there. Okay, and another is the wireline type. So wireline type normally is not used for your hydraulic engine pump, and when your operator will think that okay, I'll not remove whole tubing, so that there will be, you can install pump anywhere, and wireline will be used to retrieve or fix fixed. Okay, so this is called wireline type. So for jet pump only, okay. Open power fluid, casing free design and parallel free design. For casing free design, DSIGN, and parallel free design. Okay, in fixed insertion type, fixed insert type, actually you have one tubing, you put one macaroni, small macaroni tube, and using that macaroni tube actually you pump power fluid. Okay, and so you can get production through your annular area, or maybe that you can get production through this area, and gas can go through this, and this one can be production tubing, and power fluid is going through your macaroni tubing. Okay, so this way fixed insert type the things works. And another type can be fixed casing type. Okay, fixed casing type, like it will not have any macaroni tubing, so you are pumping here and you are getting production here. Okay, through annular. Okay, power fluid normally there will be two type of power fluid, oil power fluid and water power fluid. So what is oil power fluid? This is good lubricant, and oil means like crude oil, whatever you are getting, so normally that same thing you are injecting. Okay, so good lubricating capability is there. Okay, for hydraulic engine pump you have this oil power fluid, so it will be lubricating properly, so the friction will be lower. Okay, so good lubricating property is there, and you have hammering effect because of compressibility. Compressibility is there, so this will reduce hammering effect. Hammering effect, or water hammer, or hammering effect. You see, it is not water, so it is not water hammer, this is hammering. Hammering effect is that, like when you have a long pipe and you suddenly, and fluid is flowing, like maybe horizontal pipe or vertical pipe, doesn't matter, the fluid is continuously flowing, let's say from vertical to top or top to vertical, and suddenly you close the exit valve. So what will happen? So fluid is having its own momentum, it is moving, and you stop suddenly. Okay, so if you stop, then whole fluid will be trying to push the pipe, okay, that will create vibration, shock, the pipe can burst also. So that is called hammering effect. To avoid a hammering effect, normally people will have like accumulator will be there, or they will have some extra arrangement for such controller, so that whatever pressure pulse is there because of the fluid momentum, that can be reduced, or that can be diverted to some another piping or tubing or another hole, so that the whole system will not get broken or will not be leakage or bursting. Okay, so this oil is having good compressibility. If pump gets suddenly stopped because of certain reason, then whole fluid column should not create any other hammering effect. Okay, so this oil is good for that. Next is, okay, it is having one drawback, is that fire hazard. Okay, fire hazard can be an issue for oil as a power fluid. Water, this is not good lubricating fluid, right? Lubrication property low, lower than oil definitely. Friction loss is high. Okay, friction loss is high here. Okay, so that's why people will be looking at which is the better for certain application. Based on that, they will be selecting the power fluid. Okay, so now we'll try to go towards mathematical problems. So let's see first the formula. Okay, so let's say Q1 is engine displacement. Q1 engine, you have engine, right? And this one pump. Okay, so engine displacement and unit is barrel per day per SPM, stroke per minute. Okay, Q4 pump displacement, again barrel per day SPM. Okay, this is pump displacement. Q1 is actual power fluid displacement, actual power fluid rate, barrel per day. Q4 actual production rate, again barrel per day, and Q1 dash is theoretical power fluid rate, again barrel per day. Q4 dash theoretical production, barrel per day, B per D, small b capital B. So there is no uniformity yet, actually many books write different ways. Okay, now Q5 oil production rate, barrel per day. Q6 water production rate, again barrel per day. So Q1 by Q1 dash by Q1 equals engine end efficiency, okay, engine efficiency, and Q4 dash pump end efficiency, okay. Now Q1 equals Q1 dash by Q1 dash by Q1, okay, you can write like this. So this will give Q1 into SPM Q1 dash by Q1. Okay, and Q4 equals Q4 into Q4 dash into Q4 dash. Same thing I am writing, actually only this one changing. So this will give like Q small q4 into SPM into q4 dash. Okay, now using this formula we'll try to solve problem. Okay, you see this pump and displacement. Pump and displacement is given. Pump and displacement means Q4. Engine and displacement Q small q1. Actual production rate is Q4. Okay, so it is given in the problem that engine hydraulic efficiency Q1 dash by Q1 is 90%. Okay, 90% efficiency. Pump hydraulic efficiency 85% efficiency. Okay, now using that one you have to calculate actual fluid rate Q1 equals how much. Okay, so formula is there, SPM equals Q4 divided by Q1 by Q4 dash. Q4 equals 500 barrel per day divided by this 13.4. Q4 is given 13.4 and this ratio is 0.85. okay, so this gives 43.9 SPM. okay, and Q1 equals Q1 into SPM divided by Q1 dash by Q1. So this is giving 16.5 into 43.9 divided by 0.9. So the value becomes 805 barrel per day. Now overall efficiency. Overall efficiency, if NV overall volumetric if overall volumetric efficiency NV, then it is NV equals Q4 by Q4 dash into Q1 dash by Q1. So that gives Q4 by Q1 into Q4 by Q1. So this formula gives Q1 equals Q4 NV into Q1 Q4. So this formula is 500 Q4 dash into Q1 dash into Q4. So finally this becomes 805. okay, the same result you can get, you can use any formula. okay, now pressure calculation, how this hydraulic engine pump pressure should be calculated. First you draw one picture, closed power fluid system. So closed power fluid system is like this, it is going like this, then engine will be there, pump will be there. Engine is there, pump is there, and from engine there is one pipe going, from pump also there is one pipe going. okay, pump also one pipe going, engine also pipe going. So pump engine pipe is going to the surface, engine pipe going to the surface, pump pipe also going to the surface. Okay, this is surface. Okay, now this is my case. Okay, now engine side, this is engine, this is pump, this is surface pressure, this is PPR, surface power return back pressure. Okay, high pressure fluid is going and high pressure fluid is returning here. Okay, you see from engine, pump fluid and engine fluid is not mixing up. Okay, whatever you are pumping, the same fluid you are getting up, but pressure is changing. So surface pressure, delivery pressure PS, but when returning back it is PPR, surface pressure, whatever they have written. I'm writing as same. This is force, this is gradient G1. So okay, surface operating pressure PS, surface operating pressure, surface operating pressure, PPR is the surface power fluid return back pressure. Okay, PSI, all the units will be same unit, I am assuming. PWH, wellhead pressure. Okay, wellhead pressure. F1, F2, fluid friction. When fluid is flowing, fluid will have friction, right? Fluid friction. Okay, F3, fluid friction, F1, F2, F3 also. Okay, and G1, G2, G3, G1, G2, G3, all this gradient, fluid gradient, del P by del H, PSI by FT. Okay, and pump setting depth. What is pump setting depth? This is pump setting depth, H. Okay, H1 is pump setting depth, H1 feet. Okay, and H4 pump submergence. Submergence means, like, initially I am assuming fluid is here. Okay, so pump submergence H4, this much of fluid level is there already. So H4, P4, what is P4? P4 is here. P4 is a suction pressure actually. Suction pressure, or PWF. Okay, or flowing pressure. Now P1, now write down the formula. P1 equals H1G1, H1G1. You see this H1 means total fluid column length, H1 feet, into G, gradient. Okay, and this much of total fluid pressurizing downward, plus your surface pressure PS, and but friction force is there, so that will be negative, minus F1. Okay, P2 will be H1 G1, H1 pressure, G1 pressure. Okay, and where is P2? P2 is there in engine side. Okay, here is P2. Okay, after engine. So P2 H1 G1, it is delivering, so fluid friction will be F2 will be here. So F2 will be acting here, and G, same fluid is returning, so gradient also will be same, right? Same G1 is there, so gradient is same, H1 same, F2 is plus, and PPR, surface pressure. So when fluid is returning means pump is trying to push, friction is pushing down. Okay, so fluid column weight, friction plus surface pressure, all will be added. P3 is pump delivering P3, okay, P3 pump delivering pressure, and P3 G4 gradient, because wellbore fluid gradient is different and friction also different, okay. So P3 equals H1 G4, okay. Wellbore fluid gradient is different, that's why it is G4, and friction force also will be acting plus wellhead pressure, okay. So P wellhead will be here, okay. This is returning fluid, P wellhead pressure is here, from pump fluid is going. So P4, what is P4? P4 is suction pressure. Suction pressure means H4 G4, okay. H4 means how much liquid column is there, okay, pump submergence, whatever you said, and there will be certain okay, there is ignoring friction, okay, equals your flowing pressure PWF, okay. Now this is for closed power fluid system, closed power fluid system. Now if I have open system, okay, open system is mixing up of two fluids, inlet your power fluid and produced fluid, both are mixing up, okay. So this is going down, this is going like this, okay. So engine is this like this, engine is here, okay. So this is engine, this is pump, this is P4, and PS suction pressure same, and friction force we are assuming same, G1 we are assuming same, and P1 is here acting, okay. This is FP, this is P4 is here, and G4 is here, P3 is here, this is P2, this is G3, this is F3, this is production tubing, okay. This is power tubing, power fluid coming here, okay. Now for this one, this is open system, open power fluid system, okay. P1 equals H1G1 minus F1, friction opposite direction working, plus PS surface pressure plus fluid gradient pressure minus friction. P2 equals P3 actually, okay. So P2 from engine whatever pressure is going, and from the whatever pump pressure going out, so both are mixing up, so pressure will be same, okay. So P2 P3 is same, and P3 how to calculate? H1G3, H1 same column height, but your fluid gradient is changed, plus friction will be acting, because flow rate will be different, so friction value also will be different, plus wellhead pressure, okay. And P4 again the suction side equals H4G4 equals flowing pressure, okay. So using this one we can create some problem and I can give you, okay. Thank you very much for today's lecture. Next day we will start jet pump. Thank you very much.